This video deals with elasticity, which includes stress and strain. Okay, first of all, Hooke's law. Hooke's law says that when a force is applied to an object, the object deforms. And the equation is F is equal to K times delta L, where K is some kind of a proportionality constant that depends on what the object is and what its shape is. And delta L is going to be the amount of deformation. So it could be a increase in length, for example. Okay, so this graph over here shows a graph of the amount of stress or force on the object, and on this graph shows the amount of deformation. So in this area right here, Hooke's law is obeyed. You can see it's a straight line. So as the force is applied, the object elongates. Now in this region over here, Hooke's law still applies, but it's no longer linear. So in other words, the value of K would change slightly depending upon what the force was. Now if you get to this region over here, now you get a permanent deformation of the object. So the object does not return to its original shape. So for example, you could think of a spring, and if you take the spring and you stretch it, it's going to deform, it's going to get longer, but if you keep stretching it, you could reach a point where the spring is permanently deformed and it doesn't return back to its original shape. And then if you continue to apply a force, well then you're at the area of fracture in here, where the spring actually breaks, or the object actually breaks. Young's modulus. Okay, so exactly how much an object is going to stress when a force is applied to it depends upon some things. Obviously, it depends upon the force that's applied, and it depends upon what the original length of the object was. It varies inversely with its cross-sectional area, and there's a proportionality constant here, which we're going to call y, and this is called Young's modulus. So Young's modulus depends only on the type of material. So you go to a table in your textbook and you look up for the material, you look up the value of y, and that's what you use to in this equation. Okay, so here is the equation right here. So delta L, this is the increase in length of the object, is equal to 1 over the value of Young's modulus times F, which is the force applied, A is the cross-sectional area, and L is the original length. The units for Young's modulus here, this Y, is newtons per square meter. And I think you can see that pretty easily. If you multiply both equations here by y, you'd get y here. The units for L, delta L and L0 would cancel out, so therefore the units of y would be units of force divided by units of area. So here is a quick example. We've got a string. It's a piano wire. That's 1.6 meters long. It's made out of steel. It's got a diameter of 0.2 centimeters. We want to know how great is the tension on the wire, so that would be the force here. If the wire is stretched 0.25 centimeters when it's tightened. So we're going to use this equation, and we're going to solve for F. We want to find the tension or the force on the wire. So that's going to be delta Ly, A divided by L0. So they gave us the diameter of the wire, but we're going to need this A, the cross-sectional area. So of course that is pi r squared. Remember, we need to use r, the radius. They gave us the diameter, so that's 0.1 centimeters or 0.0010 meters. That has to be squared. So the cross-sectional area is 3.14 times 10 to the negative 6 square meters. So now we can use the formula. The increase in length is how much it stretched, 0.25 centimeters or 0.0025 meters. This is Young's modulus for steel. You can look this up on the table in your book. Here is the cross-sectional area, and then this was the original length, 1.6 meters. And so we solve for F, and it comes out to be 980 newtons. Stress is defined as force per unit area, F divided by A, with units of newtons per square meter. And strain is defined as delta L, the change in length, divided by the original length, L0. And of course, that's unitless because delta L and L0 have the same units. So therefore, we can say that the elastic modulus is equal to stress divided by strain, or this expression right here. So if you move the values around here algebraically, you'll find out that's the same equation that we saw on the previous slide. And of course, this again shows that the units for elastic modulus would be newtons per square meter because this ratio is unitless. Okay, so stress due to elongation by stretching, that's called tensile stress. And compression stress is just the opposite, and that's how the material behaves when it's compressed. So if you had a spring and you pushed it in instead of pulling it down, that would be compression stress. Now for compression stress, the same equations apply as tensile stress. So the equation that we had on the previous slide, that would apply, and the same values of the elastic modulus applies for the materials. So another example here of compression stress would be the walls of your house feel compression from the weight of the roof. And of course, in designing homes, that's obviously a very important thing to know. Weight-bearing walls, as they call them, it's important to be able to calculate and understand that the weight-bearing wall is going to be able to bear the weight of the roof. Shear modulus. A sideways force on an object is called shear, and we have an equation that relates that, very similar to the one that we have for Young's modulus. We have it right here. This diagram over here of a bookcase illustrates the meaning of these variables. So delta x would be the amount of shear. So you can see that this bookcase is a force is being applied in this direction, and it's sort of shifting to the right here. So this delta x is the amount of shear. Then S would be the shear modulus. You would look this up on a table. So assuming this would be wood, for example, you would look up the shear modulus for wood. F would be the shearing force. L0, the initial length, the height of the bookcase in this case. And A would be the cross-sectional area. Okay, so we've got a problem down here where you want to find the mass of a picture hanging from a frame, and the nail bends 1.8 times, or 1.8 micrometers. So here's the nail right here, hammered into the wall. We're applying, we're hanging a picture, and this is the weight of the picture frame. We want to find the mass, but the weight is applying the shearing force, so we'll have to solve for that. And this is the diameter of the nail. Okay, so we go back to this equation. Delta x is going to be the amount of shear, which is 1.8 micrometers, 1.8 times 10 to the negative 6 meters. S would be the shear modulus, 80 times 10 to the 9th. That's a value from the table. A is going to be in this case, the cross-sectional area of the nail. You can see right here that the nail has got a diameter of 1.5 millimeters. So we've got to compute the cross-sectional area. Pi, the radius, is 7.5 times 10 to the negative 4 meters. So that's got to be squared. So the cross-sectional area is 1.8 times 10 to the negative 6 meters squared. And then L0 is this value right here, the length of the nail that's protruding from the wall, and that's 5 millimeters, or 5 times 10 to the negative 3. I have square meters here. That should have been meters. That's a mistake. Okay, so we run through this calculation here, and we end up with a shearing force of 51 newtons. Remember, we were asked to find the mass of the picture frame. So the mass is equal to, you remember this formula from back in the earlier modules. Mass is equal to the weight divided by g. So we divide that 51 newtons by 9.8 meters per second squared, and we get 5.2 kilograms. Okay, the last kind of modulus we're going to look at is called a bulk modulus. So if an object is subjected to forces evenly from all sides, its volume is going to decrease, and we can describe the change in the volume by this equation that uses the bulk modulus. So delta V is equal to 1 divided by the bulk modulus times the pressure, the force per unit area that's being applied, and V0, which is the initial volume. Notice that this equation is very similar to the two previous ones that we have studied, the Young's modulus and the shear modulus. Okay, so here's an example. When water freezes, its volume increases by 9.05%. What is the force per unit area that the ice is capable of exerting on the walls of a container as it freezes? So notice that this is the opposite from what I was talking about here. Here I was talking about applying a force from all sides and causing its volume to decrease. But this one here is an example of something when its volume expands and the force that it applies. Okay, so the same equation is used and the same variables apply. Okay, so same equation, so we want to find out the force per unit area, or the pressure that the ice applies. That's F divided by A, and that's going to be equal to delta V over V0 times the bulk modulus. So we're told that the volume increases by 9.05%. So that's this ratio, delta V divided by V0, and of course we've got to put that in decimal form, so it's 0.0905, and then B is the bulk modulus, 2.2 times 10 to the 9th newtons per square meter. That's for water. And we calculate that the pressure, or the force per unit area, is huge, 2 times 10 to the 8th newtons per square meter. So this explains why, for example, if you don't put antifreeze in your car and you get a hard frost and all of that water in the engine block freezes, it can crack the engine block because this value is so large that it can actually cause that engine block to crack.